Nuclear fission and fusion. It's been real fun learning about this. It actually did make me want to cry, so let's get into it. I'm very excited. What is fission? Fission is the division of one nucleus into two. Pretty much all of this is going to be focused on the nucleus of an atom. So up top on the left right here, we have this lovely equation for your typical nuclear fission reaction. Obviously, there's other atoms and elements that can be used for fission, but these are the most common. So we're going to look at them. I drew a little diagram, so we're going to walk through it. You have your uranium, 235. 235 is the number of neutrons it has, and this is a really unstable isotope, which just means it doesn't like to be where it's at, and it is really reactive because it wants to change. It's naturally not a stable substance. That's why it's called an isotope. Anyways, you take this uranium-235, and if you bombard it, which just means throw a bunch of neutrons at it, it's going to absorb one of these neutrons and start our fission reaction. So after it absorbs that neutron, it is officially not uranium-235 anymore. It's uranium-236. And it's way more unstable than 235. So what does it do? It breaks apart. And it breaks apart into barium and krypton. And as you can see, I did some math right here, just adding it up. Barium and krypton have naturally 3 fewer neutrons when collectively added together than the uranium-236. So we know that those 3 neutrons are just naturally by themselves floating around. Those neutrons will actually, we're going to look at it in a second, in the right circumstances cause a chain reaction of nuclear fission, which is what produces energy. So if we look at the equation right here, we've got Q. This is the energy. Well, how do you know there's energy? Well, if we look at it, if we were to weigh this uranium right here and these 3 products, the uranium is going to weigh more than these 3 products of nuclear fission. Well, matter can't be created or destroyed, so we know that this is dissipated through heat energy. It produces a lot of heat, actually. Lots and lots of energy, and that's why we use it to create power. Now, if we want to quantify this, it's actually really simple. I bet you know how to quantify it already. That's right, Mr. E equals MC squared. We've known the equation forever, and I didn't know what it was used for until like 3 days ago. But it is the amount of energy output from a nuclear fission reaction is equal to the discrepancy mass, so the difference between uranium and barium and krypton and the 3 neutrons, times the speed of light squared. So as you can see by this equation, a really small amount of mass lost is going to produce a lot of energy because the speed of light squared is a really, really big number. It's 9 times 10 to the 16th, I think, so square that, and it's 9 times 10 to the 32nd. I think if I'm doing math right, I could very well be doing it wrong. 9 times 10 to the 32nd, though, is the speed of light squared. So even a really small amounts of mass is going to produce a lot of energy. And that's why we like nuclear fission so much, for power. So let's actually look at a nuclear reactor, which uses nuclear fission to produce electricity. I kind of got just like a little diagram here that we're going to walk through really quick. This right here is the actual reactor. And you can see it has a core. And this core, inside of it, it has fuel rods and control rods. I bet you can guess what the fuel rods put into the equation. ding, 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 if you guessed uranium fuel, you would be so correct. That is what provides the fuel into this little reaction chamber. Now, the reaction chamber also contains a moderator, which in most cases, the moderator is just water. What's a moderator, Emma? A moderator is something for these neutrons to run into and bump into, and something to slowly control and dilute this really reactive, really high energy process that's going on. So if we go back, it's not illustrated, but these 3 neutrons produced in this reaction are way, way, way higher energy than these neutrons that we use to bombard uranium. And it is 500 times less likely for these neutrons to produce a fission reaction than these neutrons because of their high energy. So the water, when these neutrons post-reaction are dashing around this water, every time they run in to a water molecule, they slow down a little bit. There's bumping around, and it slows these electrons and absorbs some of their energy so that they are more likely to create a fission reaction with uranium. Well, where does all this heat go, and how does it turn into electricity? From here on out, after it's done in here, it's pretty much is just like a steam generator. Oh, we need to talk about control rods. Control rods are what kind of they can be raised or they can be lowered. These little black things right here. And they're usually made out of boron, I think. And they also help control, along with the moderator, aka the water, help control this reaction. If they absorb neutrons, the lower they are in the reactor, the less reaction is going on. And the higher they are, the more reaction is going on with those neutrons. So we have all this heat energy being produced by fission. This heat energy is used to heat up water. Just over here in the water tank, and that water produces steam when it gets really hot, and that steam is released, and all that pressure from the steam is used to turn the turbines of a generator, which converts it into electric energy. Really simple. Once it's all been broken down, you're like, oh, that's so cool. What the heck? Anyways, we're going to move on to bombs. Another really, really not common, but widely known about use of nuclear fission. So, it's pretty much just the same thing that's going on in the reactor, except for all the control elements have been taken away and you add explosives instead. So, when this bomb has impact, this pack of explosives drives this packet of neutrons to collide with a packet of fissile material, aka uranium. And this produces an uncontrolled reaction. Lots of heat, lots of light released in the reaction, lots of radioactive material uncontrolled and blowing up. So that is why nuclear bombs are so powerful, because all that energy is being released into the air and the atmosphere, and all that radioactivity and all that stays for a long time. Anyways, nuclear bombs, really easy, really simple actually. Once you understand fission, you can understand how easy it would be to create this. Fission is the easy part. Fusion, on the other hand, is something we've been working at for a minute and we still haven't fully achieved, but it's pretty much just the exact opposite of fission. Fusion is when two molecules or two atoms are pressurized and forced together and overcome the bonds that keep them separate and forced together into a larger atom, a larger nucleus. So commonly, we use hydrogen for this, hydrogen 1 and hydrogen 2, to produce helium with 3 neutrons. So there's no byproduct, as you can do, so it's not a chain reaction like fission is. You don't have those added neutrons to create more. However, you can use the mass dissipated through heat energy that was lost, the energy lost through heat during this reaction, to fuel more reactions just like it. So the best example we have of this is the sun. All stars are powered through nuclear fusion. So that heat and that mass and that pressure at the sun's core is great enough to produce nuclear fusion. And you can see how it would be really hard to do something similar on Earth because the sun is really, really hot. But just like nuclear fission, you can use E equals mc squared, this mass discrepancy, not weight discrepancy, but the mass discrepancy between this and this to quantify the amount of energy produced. So I made a little pros and cons list of fusion. So the pros, why we keep pursuing nuclear fusion despite its scientific almost requirements to be effective on Earth, like really hot temperatures and really advanced technology, is because it doesn't produce any radioactive waste or any waste. Actually, it's the cleanest form of energy possible. Also, hydrogen is a really easy thing to manufacture and collect, and it's really abundant on Earth, far more abundant than fossil fuels or uranium. It can be taken out of water even. There are some cons, and that's that fusion occurs under enormous heat and pressure, and it's really difficult to achieve. I've said that plenty of times, but it's really hard to get fusion to happen on Earth because it's hard for us to put that amount of energy, get enough energy to replicate the core of the sun. It's still highly experimental and has not been implemented effectively as a power source for communities yet. They say it's happening soon, but like I said, we've been working on it for a minute. Excuse me. So it's somewhat of a race for clean energy. I've watched videos about nuclear fusion products and reactors in the United States, in China, in Russia, in France, happening all over the world. It's kind of like the race to get to the moon, you know? Like, we want this technology first because it's clean, effective energy. And right below it, I wrote down the minimum temperature for nuclear fusion to occur, which is 100 million degrees Celsius. That's 180 million degrees Fahrenheit, actually. And you really have to produce a miniature sun. You have to make a small star to get nuclear fusion to work. So I kind of drew what your basic reactor looks like when you're looking at all of these different trials and different people trying to create nuclear fusion. What are they doing it in? Well, this reactor is donut shaped. It's a Russian design, but it's used pretty much all over. I've seen a few nuclear reactors that, fusion reactors specifically, that it almost looks like an hourglass, and you have 2 rings of plasma on each end, and this plasma gets hotter and hotter, and when it reaches the right temperature, they fire these 2 exactly at the same time at each other. In the center, they collide, and that's where the fusion happens. And here it's a donut, so you can imagine the rings firing at each other and colliding. But the goal is to create and control what we call burning plasma. It hasn't been able to happen yet, but what we do is we use 2 really powerful magnets to keep the really, really hot plasma where it needs to be, because there's not really a material on Earth that can withstand 100 million degrees Celsius. So we use magnets to control plasma rather than using something to contain the temperatures. And this plasma flows through the donuts at hot temps, And if we could achieve burning plasma, that would mean that the heat from one plasma reaction, one nuclear fusion reaction, would cause and help maintain heat that can continue to create nuclear fusion, like the sun. It's hot enough and there's enough pressure that fusion continues to happen. However, it's still very theoretical. But yeah, that's nuclear fusion and fission. I hope I did a decent job explaining that. I feel like I did. I've tried about 7 times now, so I hope you enjoyed.